Why is water so important? Its very presence or absence can dictate the biodiversity of life in any given area. In fact, the first thing that astrobiologists look for when searching for life on other planets is water. Water makes up 60 to 70% of your own body, so while it's critical to our own mass, what is it for? Why do we need it? In this video, we will look at the chemical and physical properties of water and why it is integral to the biology of life. The first characteristic of water is that it is polar. And as mentioned previously, polar molecules are those that share electrons unevenly between atoms. The bending pattern of water molecules is due to the partial positive charge on hydrogen and partial negative charge on the oxygen end. This also creates attraction between hydrogens and oxygens on other water molecules. The polarity of water makes it possible to dissolve other polar substances like table sugar and some proteins. Molecules that can dissolve in water are called hydrophilic. Fats and oils are nonpolar and can't dissolve in water. No matter how much you try to mix the two, they will always separate. That's because fats and oils are hydrophobic. The hydrogen bonds holding water together with other water molecules is slow to take up heat and slow to release that same heat. This pretty much explains why a watch pot never boils and why there is a lag period when snow and ice melts on a 55-degree day. Because of this, slow heating and cooling for water, it prevents strong fluctuations in internal body temperatures of organisms. Water comes in three phases: liquid water, solid ice, and gaseous vapor. Evaporation occurs when water molecules absorb energy, causing them to bounce off each other, breaking apart their hydrogen bonds. When enough energy is added, water molecules will move away from the liquid and become a vaporous gas. Likewise, as water loses energy, the molecules move less and the hydrogen bonds holding water together become more linked in lattice-like structures. This forms ice. Ice is less dense than liquid water, which explains why ice floats. The slightly positive and negative charges of water molecules allows for many polar and ionic compounds to readily dissolve in water. Water acts as a solvent, or a substance capable of dissolving another substance. When sodium chloride or table salt enters water, it dissociates, or the bond holding the sodium and chloride breaks. Sodium is attracted to the partial negative charge of oxygen on water molecules, and chlorine is attracted to the partial positive charge of hydrogen on water. This allows for many different chemical reactions to occur within an organism and is one major reason you need water to live, to simply break down and dissolve many necessary chemicals that your body requires. Water is cohesive, meaning two of the same molecules easily stick together. This phenomenon is easily seen when you add water to an almost overflowing cup of water. This also explains how two drops of water easily fuse together to form one larger drop. Cohesion gives rise to surface tension, which is the capacity for a surface to withstand rupture when placed under tension or stress. Here, a piece of paper can float on water because it is light enough to not break the surface tension, but when I push it through, the paper sinks. That's because the paper is more dense than water. Water striders and even some spiders are able to walk on water because their legs are light enough to not break the surface tension. Water also can adhere to surfaces. Adhesion is the binding of two unlike molecules. This explains the slight curvature in a glass cylinder with water. Water molecules are attracted to the glass and pull along the sides, making a concave shape. Ever notice that the water level in a straw is higher than the surrounding liquid? That's because of water adhering to the plastic in the straw, causing it to climb slightly higher. Cohesion and adhesion are part of what makes it possible for massive trees to conduct water upwards from the roots to the tops of the trees. So what does this have to do with pH? pH is a measure of how acidic or alkaline a substance is. And perhaps you've measured this by your swimming pool or fish tank. Regardless, pH can have a huge impact on living things. Specifically, pH is a measure of the amount of hydrogen ions there is in a solution. That is represented by H+. Higher levels of hydrogen ions means the solution is more acidic. Lower levels of hydrogen ions means the pH is more alkaline. The pH scale runs from 0 to 14 and explains the inverse relationship between hydrogen ions and pH. 0 to 6.9 is considered acidic, with 0 being the most acidic. 7.1 to 14 is alkaline, with 14 being more alkaline, while 7 is neutral. Only pure water is neutral, and that it is neither acidic nor alkaline. Naturally, water dissociates as hydrogen ions and hydroxides, which is represented by an OH. Acids are defined as substances that provide hydrogen ions, lowering pH, while bases are substances that provide hydroxide ions and raise the pH. Let's look at a couple of examples. Gastric acid, also known as hydrochloric acid, is found in your stomach and is a very important defense mechanism for pathogens found in food. Hydrochloric acid works by, when it mixes with water, the hydrogen ions and chlorides dissociate, and with the excess hydrogen ions now available in the water, it lowers the pH, making it an acid. Sodium hydroxide does the opposite. When it dissociates in water, the sodium and the hydroxide units separate. This causes any loose hydrogen ions available to bind with that, creating water. The only downside is when you lose hydrogen ions, you raise the pH, causing the solution to become alkaline. Now, most life cannot tolerate extreme changes in pH, but contains substances called buffers, which prevent these changes from happening. In humans, we create bicarbonate ions to help prevent extremities in pH. So all those alkaline diets you read about, don't listen to them. Your body has buffers and the ability to keep pH stable all on their own. In fact, I want to demonstrate how this works. Right now, I'd like to demonstrate the power of buffers. So this is an Erlenmeyer flask filled with about 50 milliliters of water. Now, since pH color cannot be determined by the clearness of water, we're going to add a pH indicator called bromothymol blue, which will give it that bluish color that we see. Since water is around a 7.0 pH, it's going to remain blue in color, but as we get more acidic, we're going to start turning more of a green to a yellowish color. So here's water without any buffer added to it. I'm going to put 1 drop of hydrochloric acid. Notice it immediately becomes acidic. All right, this next thing I'm about to show you is going to be a pH buffer. And this pH buffer stays at a consistent pH of 7.0. Now, the reason why it's a little green in color is because the solution I use is actually yellow. But the thing that matters is that you see a color change. So this is green right now. We should expect it to turn yellow when there's an acid added to the solution. So I just went ahead, I'm gonna put 1 drop in, and I'm gonna give it a shake, nothing. I'll do another one, shake, nothing. So as you can see, this buffer is preventing the pH from fluctuating too quickly. So I keep adding drops, and it takes about 4 to 5 drops before it starts to turn into the yellow that we see. Now, bear in mind, I'm using a very powerful, strong pH called 2 molar hydrochloric acid. So the fact that it took 5 drops before it started to turn the same yellow color as water indicates that that buffer is really good at preventing the fluctuation of pH. And that's what buffers do to living systems, is to prevent that pH from fluctuating too much. Ever wonder why we breathe out CO2? Well, first, it is a waste product of ATP production. More on that later. But CO2, when mixed with water, creates carbonic acid. If you did not exhale excess CO2, this carbonic acid would dangerously lower your blood pH, a condition known as acidosis. So now that we know more about water and pH, let's take a look at the molecules most important for life.